Alright guys, I apologize, but this one's going to be in two parts. I got a phone call when I was halfway through. Just finished problem number 14, and it ended the video. So, what can you do? So I'm going to start here again on 15 and just finish it out. So this video, or this solutions video will come in two parts, which might make it easier for it to find them or might make it harder. Whatever. So we were working on problem number 15. Two charges, 7 coulomb, 14 coulomb, 1 meter apart. If the 14 coulomb charge pushes on the 7 coulomb charge with a force of 98 kN, how much force does the 7 coulomb charge push on the 14 coulomb charge? And this problem comes back to Newton's third law, right, which every force has an equal and opposite reactive force. So if the 14 coulomb charge pushes on the 7 coulomb charge with a force of 98 kN, then the 7 coulomb charge also pushes on the 14 coulomb charge with a force of 98 kN. Right? They are the same force. Now, they do go in opposite directions, but they are the same size force. All right, find the total charge of a system consisting of 111 electrons and 165 protons. So, first thing I would do here is figure out the total charge of the system in terms of E, right? That's the easiest way to do it. So, protons contribute positive charge, so 165 E. Electrons contribute negative charge, so negative 111 E. We combine those, that'll give us 165 minus 111, 54 E, right? Oops, I forgot the 4. Positive 54 E. Now, that I don't believe is the answer, or it doesn't show up in the answers, which is fine, because it wants the charge in coulombs, right? So what we have to do with this is take it and multiply it by the charge of an electron, right? That's what this E stands for, right? To get it to coulombs, we have to multiply it by E. So 54 times 1.6 times 10 to the negative 19th will give us 1.6 times 10 to the negative 19th, 8.6 times 10 to the negative 18th coulombs. All right, and that is positive because the protons, we have more protons than electrons. So positive 8.6 times 10 to the negative 18th coulombs. There's an answer in there that says 54 coulombs. If the 54 had this E next to it, then that would also be correct. But because the 54 doesn't have the E next to it, it just says 54 coulombs, it's not correct. We need to multiply it by that E in order to get the true charge. So there's number 16, or whatever number it is in years. In case 1, charge Q is at the origin and a charge 5Q is 1 meter away. In case 2, a charge Q is at the origin and a charge negative 5Q is 1 meter away. Is the size of the force exerted on the charge at the origin in case 1 greater than, less than, or equal to the size of the force exerted on that charge in case 2? So basically we have two cases, right? We have Q and we have positive 5Q, and we have Q and negative 5Q, right? And we want to know, how does the force of this one on Q compare to the force of that one on Q? Only comparing the size, right? It says, how does the size compare? The size of the force at the origin. So if we're just comparing size, right, then the positives and negatives really don't matter, because the positives and negatives tell us whether this is an attractive force or a repulsive force, right? If these are positive Q's, then this one's going to be a repulsive force. Its force will be that way. This one's going to be attractive force. Its force will be this way. But we're not asked about direction. We're just asked about size. And because we're just asked about size, right, this force is this charge and this charge are the same size. This charge and this charge are the same size. This distance is the same in both cases. So everything is the same. So the charge or the force will end up equal. Right? The force is equal to the force in case 2. They are the same size. Opposite directions, but same size. Using the table, state which object will become positively charged and which object will become negatively charged when they are rubbed together. So this time we have rabbit fur and Teflon. Again, we need to check out the table. We should see that rabbit fur is at the very top of the table with a whole bunch of plus signs. I think it was 6. Teflon is at the very bottom of the table with a whole bunch of negatives. So when we're comparing things, right, and we're trying to predict which one's going to become positive, which one's going to become negative, the one that is higher up on the table will become positive. The one that is lower down on the table will become negative, right? Regardless of how many plus signs or negative signs, these don't really matter. They don't pay a whole big, they don't really play a lot of a role. We're just looking at which one's higher on the table, that will become positive. Which one's lower on the table, that will become negative. So rabbit fur is higher, so it will become positive. Teflon is lower on the table, so it will become negative. Higher on the table, positive. Lower on the table, negative. All right. How much positive charge is in 2 moles of hydrogen? And I gave you some help here. I gave you the number of protons in a hydrogen atom and the number of atoms in a mole. So this is kind of a conversion problem. So we start out with 2 moles of hydrogen, and we want to eventually get that to charge, right? We want to get that to charge. So let's get rid of moles first, right? 1 mole of hydrogen is equal to 6.022 times 10 to the 23rd atoms of hydrogen. All right, so that'll cancel moles. So we're out of moles and we're to atoms. All right, now we know how many atoms of hydrogen that we have. So I'm going to run out of space, so I'm just going to do this math really quick. So we should get, let me just do it this way, 12.044, right? That's 2 times the 6.022 times 10 to the 23rd atoms of hydrogen. Now I want to convert that, right? Again, we eventually want to get to protons or electrons because that's how we're going to get to charge, right? So if I know the number of atoms, well, I know in 1 atom of hydrogen, there is 1 proton, right? Each hydrogen has 1 proton. So now I'm going from atoms to protons, right? I can multiply those. That times 1 is just 12.044 times 10 to the 23rd protons, right? So I went from moles to atoms. Now I'm going from atoms to protons. And then the last step, right? Since I know that 1 proton has a charge of 1.6 times 10 to the negative 19th coulombs. Now I have protons canceling, and I end up with coulombs, which is charge. So I got to multiply those two together. 12.044 times 10 to the 23rd times 1.6 times 10 to the negative 19th gives me 1.9 times 10 to the 1, 2, 3, 4, 5th times 10 to the 5th coulombs. 1.9 times 10 to the 5th coulombs worth of charge. Let me see if that shows up in the answer. Did I do it right? 1.9 times 10 to the 5th. Yeah, it shows up. All right, cool. So in these moles to charge questions, we go from moles to atoms using Avogadro's number. We go from atoms to protons using the number of protons that are in that atom, right? Hydrogen's an easy one because it has 1 proton. If we're talking about helium, it would be 2 protons. If we were talking about lithium, it would be 3 protons, right? Whatever the atomic number is, that's the conversion that you use here. And then once we know the number of protons, we can figure out the charge just by multiplying by 1.6 times 10 to the negative 19th there. What is the total electric charge of 2 kilograms of protons? So this one's a similar type of problem, except instead of starting out with moles, we're starting out with kilograms. 2 kilograms of protons. Again, we want to get to the number of protons so that we can multiply by 1.6 and get the charge. So first thing I want to do is get from kilograms to actual number of protons. So what conversion do I have that will get me from kilograms to protons? Well, I know that 1 proton has a mass of 1.673 times 10 to the negative 23rd kilograms. All right, so kilograms cancels here and here, and now I have number of protons. So I got a divider. Actually, I could probably do this in one step because I'm not going to run out of space. I know that 1 proton has a charge of 1.6 times 10 to the negative 19th coulombs. So kilograms of protons, turn it into number of protons, and then protons we can cancel to get coulombs worth of charge. So we multiply across the top, multiply across the bottom. 2 times 1.6 times 10 to the negative 19th will give us 3.2 times 10 to the negative 19th divided by 1.673 times 1 will give us 1.673 times 10 to the negative 23rd. And we can divide those 3.2 times 10 to the negative 19th divided by 1.673 times 10 to the negative 23rd. Sorry, that shouldn't be 23rd. That should be 27. Almost messed that one up. Yeah, that should be 27. Gives us 1.9 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8th. 1.9 times 10 to the 8th coulombs worth of charge in 2 kilograms. And that shows up. All right, so there we are, 1.9 times 10 to the 8th coulombs in 2 kilograms worth of charge. Go from kilograms, use the conversion of the number, or the mass of a proton, right? 1 proton is 1.673 times 10 to the 27th, negative 27th kilograms. And then we use the conversion of protons. 1 proton is 1.6 times 10 to the negative 19th coulombs worth of charge. All right, rank the system in order of increasing size of the electric force. So we're given a Q1, a Q2, and an R, and then we want to rank those in terms of increasing size, which means from least to greatest, of the electric force. So we basically want to use Coulomb's law on all of these, right? K times Q1 times Q2 over R squared. So that's really what I'm going to do. Let's take A, K times Q1 times Q2 over R squared. That will give me 2K, right? 1 times 2 is 2 divided by 1, yeah. So that'll give me 2 times K for A. If we look at B, again, I'm not going to multiply by the K because each one will be multiplied by K, so it doesn't really have an impact. K times -2. Negative sign doesn't matter because we're using absolute values. 2 times 4 divided by 3 squared. That will give me 8/9 times K. We look at C, K, 5 divided by 5 squared. That'll give me 25 over 25, so 1 times K. And D, 16, okay, times 16 times 3 divided by 4 squared. 4 squared is 16, so 16 and 16 cancel, and we get 3K. So our order here, least to greatest, right? B is the smallest, D is the largest, so we would go B is less than C, which is less than A, which is less than D. And there is our order from least to greatest. Cool. We're on a roll. We got 3 left. Using the table, state which becomes positively charged and which becomes negatively charged when they are rubbed together. This time we have PVC and cotton. I'm going to have to go back and look at the table because I forget which one of these is higher up. All right, so cotton has a single minus sign with it. PVC is down lower. It has 5 minus signs. So again, minus sign doesn't really matter. What's important is which one is higher on the table. So because cotton is higher on the table, it's going to become positively charged. PVC is lower on the table, so it will become negatively charged. So cotton will become positive because it's higher on the table. It wants to take electron, right? It still wants to be negatively charged, but because it wants to be negatively charged less than PVC wants to be negatively charged, it will end up becoming positively charged. So cotton becomes positive and PVC becomes negative. So it's all about which one is higher on the table and which one is lower on the table. The higher one will become positive, the lower one will become negative. A charged rod is brought near a suspended object. The object is attracted to the rod. Based on the interaction, we can conclude that the suspended object must have an electric charge. So this was another true-false one. And we talked about this case earlier with repulsion, right? The object was repelled from the rod, and we concluded that that was true. It must have an electric charge. In this case, we're going to see that something different is the case. So when we have objects attracting, right? Let's just throw out the scenarios here, right? Here's my rod, let's say it's positively charged. We have a suspended object. Right? The suspended object might be negative, then they would definitely attract, right? Or we could have a negatively charged rod, and if the suspended object was positive, then they would attract, right? So in these two cases, yes, the suspended object is charged, but is that always the case? And the answer is no, because of polarization. Right? And we talked about polarization in the PowerPoint. In polarization, a neutral object or a neutral conductor can attract to a charged object. Right? So because of polarization, we could have a scenario like this where we had something that's positive and something that was initially neutral, right? So positive, negative, negative, positive, right? So this was neutral because it has the same amount of positives as negatives. If it's a conductor, these electrons can shift over and we end up with something that looks like this, where the negatives are all on one side, right? Positives end up on the other side. And because the negatives have shifted over, these now attract, right? And the converse is true for negative charges, right? If this was negative, the electrons would move to the other side. We would end up with positives over here, and the positives would attract. So because of polarization, we can have a neutral object attracting to a charged object. So can we say that if there is an attraction, those objects have to both be charged? The answer is no, because we could have, right, this is a neutral object, right? It has the same amount of positives as negatives, and it can attract to a charged object. So this one is false because we have this phenomena called polarization, right? Polarization messes that up because neutral things can attract to charged things. So repulsion, we know it has to be charged because there is no polarization effect for repulsion. Polarization is always attractive. So if the two things are repelling, we know that they both have to be charged. But if the two things are attracting, we can't be certain that they are charged because it could be attracting by polarization. At what separation will the electric force between charges of 2.1 microcoulombs and 5.0 microcoulombs have a value of 2.5 newtons? I pressed a little too hard on the other side there. So let's list out what we've got. Force is 0.25. Q1 we'll say is the 2.1 microcoulombs. Q2 we'll say is the 5.0 microcoulombs. We have K, which is 8.99 times 10 to the 9th. And we are looking for the separation. We're looking for that R value. How far apart are they? So we start with our Coulomb's law. F equals K, Q1, Q2 over R squared. We plug everything in. I probably should have gone down another one. 8.99 times 10 to the 9th. 2.1 times 10 to the negative 6th. 5.0 times 10 to the negative 6th. divided by r squared. I forgot to plug in my F too. All right, so we'll multiply across the top. 8.99 times 10 to the 9th times 2.1 times 10 to the negative 6th times 5.0 times 10 to the negative 6th gives us 0.094. So I'll get F, I know, is 0.25 equals 0.094 over r squared. And at this point, we just got to solve. So we got to get this out of the denominator if we're going to solve. So multiply it up to the other side. 0.25 r squared equals 0.094. We got to divide by the 0.25 to get the r squared by itself. So we get r squared equals 0.378. And then we take the square root. And we get r will equal 0.61 meters. There is our r value, 0.61 meters. All right, easy. We figure out what we've got, plug it into our Coulomb's law equation, which is really the only equation for this section, and we go ahead and we solve. All right, last two, right? Yep. System consists of electrons and protons. It contains 120 electrons and has a total charge of positive 130. How many protons does it contain? So we know we have a charge of negative 120 E because of the electrons. We know the total is positive 130 E. So how do we get from negative 120 to positive 130? Well, we have to have at least 120, right? 120 protons will cancel out the 120 electrons, and then we have to have an additional 130 protons to cancel or to get to this charge of 130. So the total amount of protons we have to have is 250 protons, right? 120 of those will cancel out with the electrons, and then the additional 130 will contribute to that total charge of plus 130 E. 250 protons. And last but not least, which statement is true for an object that is electrically neutral? Does it have zero charge? Does it have the same amount of positive and negative charge? Or we aren't sure. So neutral, I like to be a little particular that neutral is not zero charge. There are very few things that actually have legitimately zero charge. I can actually only think of one thing that has legitimately zero charge. It is a neutron, right? Every other thing has the same amount of positives and negative charges, and that's why it's neutral, right? Neutral doesn't mean no charge at all, right? Everything has positives and negative charges. It's whether they balance out is what gives us something neutral, or they don't balance out, that gives us positives or negatives. So zero charge is not a thing, all right? Everything has positives and negative charges, but do they balance out? If they balance out, then we end up with neutral. If they don't balance out, then we end up with positive, or we end up with negative. All right, and that is number 26, which takes us all the way through the review. Like I said, I apologize if you got to search through this a little bit to kind of find the questions you have, or the problems you have questions about. I think in the future, for the reviews at least, I'll put them so they don't switch orders, which should make it a little bit easier for us. All right.